Hello, I'm here to talk to you about what I think the largest problem of science is today, and what I think a solution might be to that, and more importantly, what I think that I can do to try to fix this problem. So what is this problem? And I should specify that it is an outreach problem, because there are lots of problems in a variety of different aspects regarding science, but I think the largest outreach problem is that there is a knowledge gap between scientists and non-scientists, and this is particularly evident if you look at news articles and how they compare with scientific articles. So why do I think this was happening? And I think this is because there's no easy, free method to learn science. So after you get out of grade school, it's rather difficult to actually find out and learn science. And there's really no way to find out answers to specific questions either. So if you don't care about learning all of the physics of how light interacts, it's sort of challenging to really understand how the sun interacts with the atmosphere and makes the sky blue, for example. And so what is the solution? I think that a solution that if you were going to make it, it has to cover all education levels. So it can't just be scientists and it can't just be for the public. It has to bridge that gap. It has to answer a targeted question. You have to be able to ask a question like why the sky is blue and give a definite answer that's understandable. And lastly, you have to be able to have a solution that is accessible by a large amount of people. It does no good if you create resources online and no one's able to find it. So what is my solution? Well, I think that the correct answer is to make YouTube videos. If this is of interest to you, I'm going to be talking about what I've just covered in more detail. If not, thank you for watching. As I said before, what I think the largest problem is in science is this gap between scientists and non-scientists. And this starts back at grade school. Grade school is pretty much the last time that everyone in all professions is taught science. They're taught biology, ecology, physics, chemistry, geology. That's the last time that everyone has the opportunity to learn all of science together. Of course, this varies country to country, but in general, you graduate grade school with an introductory knowledge of all different fields. After that, you can either take more focused science education in the form of STEM classes at various universities, or you can do anything else. And by anything else, I mean you can be a pilot, or a construction worker, or a farmer, or join the military. And you may come across some science in your daily life as well. Even if you aren't trying to learn about science in a classroom setting, there's an example of the black hole just a little bit ago that was all over the news because it was the first time they managed to photograph it. Or if you are active in following the news, you can see all these articles about things that the journalists think that people would like to read. So the effects of coffee on you, or a new species of cat they found. But the thing is that most people really haven't studied science since grade school, and this actually is true for a lesser extent for people in the STEM field. And that's because STEM is a very diverse field. You have astronomy with mathematics, with genetics, and it doesn't make sense for a scientist to study both astronomy and genetics. They're both interesting fields within their own right, but understanding planetary motion has not much to do with a specific gene in a flatworm, for example. And so you end up becoming super focused on a specific field, but all the scientists are related in various ways. I mean, there's this comic by XKCD that shows how all the different sciences sort of feed into each other. Even at an individual level, you can have an ecosystem that has rocks interacting with biology, interacting with oceanography, interacting with the atmosphere. No science is really independent, but everyone's sort of focused on their own field. So let's say you want to learn more about science as a scientist or a non-scientist. How do you find out more? You can read a book from a library. It's a free way of gaining knowledge. You can do it at a university or your public library, and you can get more background about a scientific information. You can also look online. There's courses available from various universities that they've recorded lectures and posted online. MIT, I know, has rather good ones in engineering and several different sciences, mathematics, biology. or you can go to this website that I've posted, which is a fabulous resource. It sort of presents all of the open access resources from various universities around the world. So there's ones from Harvard, Yale, Oxford, a couple in Australia, and all over. And they teach you stuff like history or architecture beyond just STEM fields. It's completely free, and they are not paying me anything to advocate this in any way, shape, or form. I think it's just a great resource if you are interested in taking a class in a specific field, that they might have videos that are applicable to that. And there's a lot of other resources, but these are very general resources. They don't answer a specific question. So how do you actually do that? Well, the easiest answer is go on the internet and type it in. I am in oceanography, so I've chosen a specific question in oceanography. What is an eddy? And an eddy is a fundamental concept. You learn it in any introductory to oceanography class at an undergrad level. If you take the first class, sooner or later they'll answer it. It's up with ocean current and how waves work and that sort of thing. So what do you actually get when you search it on the internet? Well, the first and the third video are both talking about river eddies, which operate in similar ways, but are not really applicable to oceanography. The second video is applicable, but it's only presenting the motion of one in a wave tank, which is cool, but it isn't explaining how that eddy works or really telling you what it is. Now, the first search result, the NOAA, and if you're not from the US, NOAA means National Oceanic and Atmospheric Administration. This is exactly what we're looking for, and it explains what an actual eddy is and how it operates in the ocean. The one problem with this is that the language isn't always the most accessible if you have not much scientific background. For example, you might not know what a picnic line is. I've chosen picnic line out of this page because it is the simplest concept that someone might not be aware of. I could have just as easily chosen any of the other things I've circled. In particular, that red box, MEDI, is something that I was not aware of when I was originally looking this up. It's a very specific type of eddy, and so I'm not entirely sure why they put it on a general page, but perhaps one of the authors specifically focuses on MEDI, and since it is his field of research, he thought that it was necessary to put it on this. So if you search up what is a picnic line, you get the answer right off the bat. A dictionary pops up and it tells you that a picnic line is a layer in the ocean that the density changes very quickly relative to the depth. But what if you didn't want just this and wanted to know how that affects the ocean? If you look at the next results, you'll find that the first one is a book excerpt, the second one is a Wikipedia article, the third one is from NASA, and the fourth one is the one I want to focus your attention to. The first three do actually answer the question very well, but the fourth one, when you open it, it's actually a 12-page document talking about how you can teach these concepts to a classroom. And how this is different is that now you're going to have to look through the entire article to try to figure out what a picnic line is and read a bunch of stuff that isn't necessarily related to what you're doing. Now, if we continue looking it up, you can see that there's 2 research papers and a class. And you can notice it's a class because of the class number. All 3 of these resources you're going to have to read in more details, similar to the educational materials provided by NOAA. Of these 3 resources, the class materials is probably the most likely to answer your question in full, since this is a more general concept in oceanography. Both of the research papers are going to give you more information than is necessary. For example, the last search result that I've listed, Picnic Line Development and Its Consequences, is a formal research paper which talks about how the in-depth mechanics of how the picnic line changes and what it affects in the environment, which is an interesting paper. And if you're going to be studying picnic lines in a greater application, this is definitely useful for you to read. But if you're just wondering what is a picnic line so you can go back and continue reading the eddy paper, the research papers are going to give you much more detail in a tangent compared to what you're actually looking for. So what if we look at something that's more complicated than a picnic line? Picnic line could be easily answered by a dictionary definition. What if we look at something like geostrophic balance? And the reason why I've chosen geostrophic balance is because this is the actual physics behind the major forces that influence the eddy. And this is really important to understand why the eddies persist and why they act the way that they do. So if we search geostrophic balance, what do we get? We get a book, 2 Wikipedia articles, a list of books, which is not very helpful, and a whole slew of class materials. And these class materials come in 2 different forms. The first form is class notes, which will provide all of the information necessary to understand a given subject that the person taught in class. So it's usually one class notes per lecture. These are very useful, especially in terms of mathematical equations, but there is a lot of reading, and they tend to be very dense because you don't necessarily have access in the prior class notes. You just have this page that popped up on your search results. And you can notice that this is about 10 pages long. The other form that it comes in is in slideshows. And slideshows can be useful because, again, they'll present the equations and they'll present images of the concepts, but you're lacking the oral narration and a lot of the supporting material, like the prior reading that they told in class. So this can be very unuseful because if it's following the presenting style that you just show something on the board and spend a lot of time talking about it and perhaps writing on a blackboard to illustrate the concepts, this can be quite difficult to understand just from the class slides. So what do we have from our search results? We have Wikipedia, we have textbooks, we have dictionaries, class notes, class slideshows, and research papers. The least helpful of all of these is the textbooks because they're long, hundreds of pages, and are almost always restricted. With the exception of the excerpts, you're almost always going to have to purchase the book to read the book, and if the part that you're trying to read is not in the first chapter, you'll have to pay that fee. The next one that probably is not very helpful is research papers, not because research papers don't contain a lot of good information, they absolutely do, but if you're looking for the answer to a targeted question, research papers usually don't do that. Research papers are usually a case study, and so they're off topic or more advanced than is necessarily needed to answer a question. So if we talked about, say, the picnic line or geostrophic balance, it would be a paper that would have that word in it and reference it in their introduction or in a conclusion, but most of the paper would be sampling or the equations of motion and using these two concepts to build on a larger concept or in a very specific application. The next one that's not as helpful is dictionaries, typically because they are short, and because they're short, they can either be not exactly what you're talking about. So like in an eddy, there's ocean eddies and river eddies. They act very differently between the two and are caused by different processes. But if you look up a dictionary definition, it might just have one definition, the other definition, or neither, and just be a general definition. The last one that I would avoid is these class slideshows, and unfortunately you can't avoid them just by looking at the class description because you open it and then it slides. But these are missing the oral information that actually allow the slideshow to effectively communicate a concept to a class. The last two are winners, and these are the things that I would recommend if you're going to be researching things on your own. So what happens if you look at those Wikipedia results? Because I mentioned before that there were two. For geostrophic balance, the two ones were geostrophic current and geostrophic wind. Both of these are applications of the geostrophic balance, one to ocean currents and one to a more advanced topic that I will not get into at this time. If you look at them, you will find the geostrophic balance written in the articles. But if you try to understand how they actually are formulated, then you have a bit of a problem because they both reference each other. And so you actually have to combine the two of them to get a complete derivation and then be able to understand why this equation is the way that it is. So what is the video this far? Most people have not taken science since grade school, and that science can be difficult to learn, and this is one of the major reasons why there is this gap between scientists and non-scientists. So what can you do to try to fix this? And I've mentioned the requirements before. I'll cover them in a bit more detail right now. First, they have to cover all education levels, which is pretty obvious. This is necessary to bridge the gap between grade school and a PhD level scientist. It has to answer targeted questions such as what is a picnic line and what is an eddy and what is the geostrophic balance in such a way that if someone types in that, they'll be able to find a resource that will give them an answer without having to read through a large amount of literature. And the last thing is that it has to be accessible in order for people to actually get anything from this. As I mentioned before, the solution does no good if it's buried within 100 search results and no one can ever find it. So what's my solution? Teach science on YouTube. And what I mean by this is that I'm going to pick a field of science, and the first one is going to be oceanography, since that is the one that I am most familiar with, and I'm going to ask a series of questions that will teach the core concepts of oceanography, but then you can combine all of them to get an overarching understanding of oceanography. And so here's a list of questions that I will likely answer in my upcoming videos, which should, if you can combine them all, give you some understanding of the chemistry of the ocean, the physics of the ocean, the biology of the ocean, and how they all interact to create oceanography and create what we see in the ocean. Now, this has to be applicable to all education levels, and I'm going to do this by having different classes that are all applicable to different education levels. So the first one is beginner, and that will be applicable to people who are in grade school or have completed grade school and have an interest in oceanography. Now, if you're relating this to things that are currently on YouTube, it'd be something along the complexity of Crash Course, which they endeavor to teach a general background into a specific subject. Now, these are particularly good if you're taking grade school and you're in an advanced placement or honors class. These are great for studying for a final exam or take a test to get college credit, but they don't really answer specific questions. The next stage would be intermediate, which would be similar to a bachelor's degree or undergraduate education. It's someone who's learned all the core concepts of oceanography and would like a more detailed understanding of how the ocean works. And this would be similar to something like Numberphile, where you actually do need to have some understanding of mathematics in order to get the most out of their videos. The next stage would be advanced, and by this point it's anything in higher education, and it'd be something along the lines of individual scientists and their channels on YouTube. So for example, Paul Beckwith studies climate change and atmospheric science and talks about in his videos how the global atmospheric circulation sort of changes with time. The next class will be for instrumentation, and I'm imagining this as for people who have already some understanding of oceanography, and the reason why is because it's going to be a brief overview of a scientific instrument that's currently deployed in the field and how it works and how you deploy it and how you process the data. The reason why it'd be for a more advanced audience is because you'd have to understand what a plankton is in order to fully understand what a plankton net is doing. And this is talked about primarily by oceanographic institutes. So Woods Hole Oceanographic Institute has made a series of videos about stuff with sound, or with Alvin, which is a deep sea submersible. But what the majority of these videos are, I'm not pointing at Woods Hole specifically, but they tend to be more of deploying and retrieval rather than actually how the instrumentation works. You can actually find lots of these videos online. Scripps is another major oceanographic institute that does talk to some extent about how instrumentation works. In their case, it's primarily focused on ocean robotics, and there's a whole variety of other science labs and institutions around the globe that do some of this sort of live research. Lastly, I want to talk about how to actually work with scientific data. I have run into a problem before when I've got a new data set of how to actually look at the data. So if I have satellite imagery and I'm trying to apply this to my research, and I'm not a satellite scientist and my advisor is not a satellite scientist, how do you actually learn how to process satellite data? Well, there are some resources. For example, this is a conference talk about how to work with satellite data, but there isn't really a short, concise way of saying this is what you have to do when, this is what the variable is called, this is what this. Generally, you have to refer back to manuals, and there are PDFs that sort of teach you how to go step through step, but I think that it would be much easier if there was something along the lines of a video that's demonstrating how you actually work this. I know that there's lots of videos like that for how to use various programs in other non-science applications, so like video editing or something like that, but there isn't really a whole lot to do with science, and so I'm going to make the fifth class be a technical class focusing on this sort of thing. I believe that this covers all the different education levels, and I might adjust these classifications if I think it's necessary later and that there's some intermediate stage, but I think this covers almost all the science material that I will be posting on this channel. As I mentioned before, these questions have to be targeted, and by targeted I mean something along the lines of the questions I posed before. So introductory questions would be covering the basic concepts of oceanography. So what waves are, what optical properties the water has that make it blue, what are tides, what are plankton, that sort of thing. Intermediate stage would be sort of applying those concepts and coming up with more specific examples of how this actually plays out in the ocean. So for example, the Redfield ratio is dictating what specific nutrient concentrations a plankton needs to grow, and that video will talk about how variations in this ratio impacts a biological community in the ocean and what that can tell you about things living in the ocean. The advanced class would then fill all of the gaps, so that's pretty much anything that would be applicable to a scientist working now. So for example, I refer back back to resources whenever I'm talking about Kelvin and Rossby waves, because the equations of motion of Kelvin and Rossby waves are more complicated than, say, a simple wave that you see on the beach. And so these are more resources that would be applicable for people who are working towards higher education. Definitely the Navier-Stokes equation and how to manipulate that will be covered. All three of these are all more physics applications, but I'll talk about chemistry and biology as well. So if you look at a targeted question from the beginner class, how deep is the ocean? It's going to be one of the first or second videos that I make in that class, because I think it's very important to see how the bathymetry actually interacts with the surrounding ocean and how changes of bathymetry cause change in the ocean. Now, if you look up this question on YouTube, you do get 3 videos. It's been answered, or has it? The first 2 videos, they're useful. They actually put it into proportion of what things happen when, and they're relatively short. If you look at both of them, they're fairly good. This last one, though, is over 17 minutes long, and I'm going to tell you right now the answer to this question at risk of you not watching my video. The answer to how deep the ocean is actually 2 different numbers depending on what you're thinking about. If you're thinking about the absolute deepest point, like these videos do, then you care about Challenger's Deep, which is the bottom of the deepest oceanic trench in the world. But if you care about how deep most of the ocean is, it's only about 3 or 4 kilometers. That's a big difference between 11 kilometers and about 3. So I have a problem with this because it doesn't really teach an oceanographic concept of what the actual average depth of the ocean is. It's instead teach extremes, and I don't believe that that's quite accurate. But this 17-minute long one is particularly bothersome to me because of how they did it. So the entire video consists of trivia, like what happens at certain depths. So at this depth, this is the deepest that such and such whale can dive to, or this is the deepest that a free diver could reach, which again, it's interesting for perspective, but there's a problem, and that is that not all their information is correct. A lot of it appears to be just taken from other videos of similar nature, or that they've done their research and just misinterpreted what it was about. And I'm not really hating on their video specifically. I find this is a pretty common problem across most of these questions, that they present it in such a fashion that it does sort of answer the question, but then if you fact check them against science, it might not be correct. The thing that was really alarming about this video is that it talked about the max depth that a human can dive to before they start having problems with like gases in their blood. And the major reason why that's problematic to me is because it gives the assumption that you don't have problems before that. And the major problem with that to me is that you can get problems with that at any depth because it's an ascension issue. It's how quickly you change depth rather than a hard depth limit. And if you misunderstand that and you go scuba diving, that could lead to you dying. And I find that very alarming. So I just wanted to point that out. The last thing is that these videos have to be accessible, the videos that I make. And the reason why I chose YouTube is exactly for this reason. If you remember back to when we were talking about eddies, right at the start is videos of what an eddy is. And so while this might not be the most relevant for eddies because there's lots of videos that have already been released, in some of the more specific aspects like what is geostrophic balance, it's sort of crucial. If I put my video on YouTube, then it will be one of the first search results, and so that is very useful for this being an actual solution to the problem. The second reason is that YouTube allows playlists, and what this can do for me is that I can answer a specific question but make a playlist of all the questions to combine them into one course that you could watch all the way through and get an understanding of that level of a particular field of science. If you watch, say, an introductory level all the way through, you should be ready to start watching intermediate levels. And then once you get through that, you can start to approach an advanced level. The last reason why I chose YouTube was because of the subscribe function. And I find that is a very helpful aspect because a lot of these websites, even if they've got tons and tons of good information, you need some sort of RSS feed or email list to get information from it. On YouTube, if you subscribe to something, then when it updates, if you hit the little bell, then when it updates, you do get an update. And I think that that is a very important resource to increase the accessibility of this YouTube channel. In closing, I'm going to start with beginner oceanography and I'm going to work upwards from there so that hopefully people that are watching my videos can sort of grow and understand the introductory concepts before I move on to the next level. The first episode should be right around the end of July in 2019, and thank you for watching, and please leave any comments, positive or negative, about this video below. I do read all of the comments, and I would be very interested to see what you guys have to say. Thank you.